Well, first of all, thank you for, very much for inviting me to this very nice workshop, and thanks for a nice introduction. So what I will present here is basically what I did in my PhD. So I defended roughly 1 month ago. So this is basically my disputation. So when I started out with my PhD roughly 3 years ago, the CO2 concentration was around 408 ppm. And in the first month, actually, the CO2 concentration decreased. And a few months later, it increased again. So this is what is known as the CO2 seasonal cycle. And it's not a phenomenon that only happened in the first year of my PhD. Actually, this is something that reoccurs every year. And as I said, it's known as the seasonal cycle of CO2. And it is controlled by plants. So in summer, they make photosynthesis and they draw CO2 down. And in autumn and winter, the ecosystem is respiring and CO2 is coming back to the atmosphere. But besides the fluctuations, you also see the steady increase of CO2, and that is caused by human CO2 emissions. There's one scientist who really did a lot in this with the CO2 concentrations, and that is Charles David Keeling. He started with CO2 measurements back in the 50s, and he also was among the first scientists to warn society that increasing CO2 will have an impact on our climate and on the Earth system. So one thing he found out actually is that the vegetation or ecosystems are getting more productive. So he used these CO2 measurements and looked into the CO2 amplitude, which is a proxy for the ecosystems, and he found out that in summer we see that the CO2 is actually being drawn down. So I don't have a pointer here, but you see here compared, so this is an updated figure, but when he did the work, he basically compared recent CO2 measurements with the ones he made very early in the year, early in the period, and what they found is actually in summer that the CO2 minimum is actually being drawn down. And from that, he and his colleagues, they followed that that the terrestrial biosphere has taken up more CO2. A year later, a young postdoc back then called Ranga Mainini joined the group, and he brought the first remote sensing data set, and they looked into if they can find this increased activity of the terrestrial biosphere also in the remote sensing data, and indeed they did, and they found out that the Earth is greening, and we already had that topic earlier today. After many decades of research, the drivers behind this greening trend is still unknown. So there was this year one paper by Chen et al., and they said that actually that most of the greening we see, or the greening we see in regions where we have a lot of croplands, is actually due to land management. But if we look into natural vegetation, the drivers are still unknown. And there was a few years back one publication, and they said that actually 70% of the Earth's greening trend is sort of due to CO2 fertilization. We also had heard this term already today. But why is it so important to look into this? So 30% of the anthropogenic carbon emissions are actually being absorbed by terrestrial ecosystems. To give an idea how much that is roughly all the CO2 that was emitted due to the burning of coal was basically absorbed by the land by the terrestrial ecosystems. Now, if we look into the future projections, so here I show you a plot of Friedrichstein et al., and it is the cumulated land flux, so how much carbon is been uptaken or is sort of interacted with the atmosphere, and I show all the models from this CEB T4, from this intercomparison studies, and you see that they are all over the place in 2100, and they don't even agree on the sign. So we see sort of models that show that the land will actually be a source of carbon at some point, and then there are models that show, well, a lot of carbon will be taken up by the land. So there's a huge uncertainty in future projections. And in this context, I formulated my research questions. And one is, so what is driving the observed greening trend of the natural vegetation? And my second question was, can we use this greening we get from the observations to get a better idea of the uncertainty in the carbon fixation by plants in the future, which is a very important thing to know if we want to talk about climate change and how we can sort of counteract, or how can we mitigate climatic changes. So first I will focus on the first question. So what I did is I analyzed multi-decadal satellite observations. Then I used model simulations to disentangle the different effects of CO2. And then I used a new method for climate scientists that is called causal theory, to make a driver attribution not only on biome scale, or not only on global scale, but also on biome scale. So, but first, before I show you my result, I want to talk about how actually is CO2 affecting plants. So there are basically two effects. So one is the physiological effect of CO2, and there's the radiative effect of CO2. So the radiative effect of CO2 is very prominent. It is basically climate change. But if CO2 also has an effect directly on the physiology of plants, and one is the stimulation of carbon fixation. So if we look into the leaf interior, there is an enzyme called rubisco, and it is the most abundant enzyme on Earth. And it can either do photorespiration or carbon assimilation. And it does photorespiration due to using O2, and it can do carbon assimilation using CO2. And O2 and CO2 basically compete on what rubisco is doing. So with increasing CO2, naturally also carbon assimilation will increase. And there's the second effect that already was a topic in the earlier talk today, and that is the water use efficiency effect. So we have the leaves, and they have little openings called stomata to regulate the gas exchange with the atmosphere. And with rising CO2, they sort of adapt to the CO2 enriched atmosphere and lower the conductance of the stomata, and thereby lose less water, and thereby they can be more productive. So where the CO2 fertilization effect is sort of acting positively on plant productivity, climatic changes can go either way. So basically, if we have climatic changes, or if the radiative effect of CO2 can sort of have an impact on temperature, which is, you know, a very important topic in many other studies. But it can also have an effect on precipitation patterns, and as well as on cloudiness, and thereby regulate the radiation that reaches the surface, which is an important factor also for plant productivity. So as I said, it can go in both directions. So it can either have an increasing effect on plant productivity, for example, due to warming in the northern high latitudes, or also, for example, increased rainfall. But it can also have a declining effect. So, for example, it can induce a drying trend, or due to disturbances such as droughts or heat waves, plant productivity can also go down. So I said that I combine observations and models. Now, how can we observe plant productivity? So we do this using satellites. And most of the satellites actually look into spectral reflectances. So we have the sun that emits radiation, and there's one spectral range in this radiation that we are interested in, and that is the photosynthetically active radiation, which is between 400 and 700 nanometers. And it goes down to the surface, and there are leaves, and they absorb some of this radiation, and another part goes back up. And if we plug in our satellite in between, we can sort of get a measurement of how the fraction of absorbed PAR, and that is a good proxy for plant productivity. So from satellite observations, we get an idea of vegetation greenness or plant productivity based on the surface spectral reflectances. Models, however, they don't provide us such knowledge, or most of the models don't. They use the leaf area index, and that is abbreviated as LAI, and it's defined as the leaf area per unit ground area. So, and to combine the two, to combine the satellites and the models, I use observational-based data set that is sort of providing LAI based on this spectral reflectances. So when I talk about greening or browning, it is maybe, yeah, so you can look into the plant productivity, and if you have a long-standing significant increasing trend, we talk about greening, and if we have a long-standing significant decreasing trend, we call it browning. And we test significance using this Mann-Kendall test. So now let's see how it looks if we take the satellite observations that go back to, until the 80s, and in this time CO2 increased about 65 ppm. And here I show now these patterns of greening and browning that we get from this data set. So here I show the significant trend in annual average LAI in percentage per decade for each pixel. And I mask out regions which are heavily used by humans. So you see the white mask in North America, also here in China and India. So because we're only interested in how the natural vegetation responds to CO2. And we find that 54% of Earth's natural vegetation exhibits significant trends. And 40% of it is greening, whereas 14% of it is browning. So I said that we want to know exactly what is driving the change. Only from the observations we don't get this information. So we need models. And here I show you what kind of simulations we need to get an idea of the drivers of greening and browning. So the model simulations I did is, first I made a control run. So I have our very sophisticated Earth system model, and we just let it run at pre-industrial conditions to get an idea how does the system sort of react when it is not forced with CO2 emissions or any other kind of forcing. Then I made a historical simulations with all the forcings we know of. So increasing greenhouse gases or deforestation patterns or volcanic eruptions. So everything we know, we put in our model and see what the model tells us about the historical period. Now, to get an idea of the different effects of CO2, I make historical runs, but I always switch off the effect I'm interested in. So I make historical runs without, for example, the physiological effect of CO2, and I call it no PE. Then the radiative effect of CO2, no RE, and then I made simulations where I turn off both effects of CO2. I use our Earth system model that we developed at the Max-Planck-Institute in Hamburg, the MPI-ESM, which is a fully coupled Earth system model. So it has an ocean, a land, and an atmosphere component, and they interact. And as I said, I make historical simulations, and I make these experiments with different initial conditions. So I get an idea of internal variability, and this is what we call an ensemble. So I make an ensemble of 6 realizations. And besides that, I also use a collection of many land surface models. And this is called the trendy ensemble. And this is, so the big difference to the MPI-ESM here is that it is actually driven with observed climate. So they just plug in what was being observed in the last century, and they just see how the land surface reacts to these forcings. And here we have an ensemble of 13 different models. So we get an idea from the models how the CO2 is somehow affecting the land surface. But we need to somehow attribute the change. So to get an idea, can we really find the driver of a greening or browning pattern in specific areas? So what I did is I used the causal theory, and that allows me to make sort of an attribution in a probabilistic setting. So I asked the question, what is the probability that a given forcing, for example, the physiological effect of CO2, has caused a long-term change in the system? So has it caused a greening or browning? And in this setup, I need to formulate 3 different facets of causation. One is the necessary causation, the second one is sufficient causation, and then causation of necessary and sufficiency combined. And I will use electrical circuits to illustrate that. So here we define our event, that is the occurrence.
It would be nice if you give the original reference to the theory linked to
Pearl?
Yeah, Pearl.
Yeah, okay, I should do that, yes. Yeah, so there was Pearl 2000. No.
He's from UCLA.
Yeah, and it was the book was from 2009.
The book
no?
is, I think,
very
causality theory, but I mean, you know, he got the Turing medal for this.
Yes,
so
yeah, you're right.
it's more than the book, but that's a convenient reference.
Yeah, okay. But it is, of course, the citation is in this citation. But you're right. For the next slide, for my next talk, I will put it there. So I will use electrical circuits to illustrate the idea of these 3 different facets of probability. So here, the light bulb is defined as the event, so the occurrence of a long-term change in the system. For example, in my case, it is greening. And the different switches represent different causes. So here, PE and RE for the radiative and the physiological effect. And in the case of necessary causation, both of the switches are needed so that the light bulb goes on. In the sufficient causation, they are in parallel, so each of the causes can sort of cause the light bulb to go on, but you know, there is no necessary condition in this electrical circuit. So if we combine the two, we have here the radiative effect, so that the red switch that sort of brings the light bulb to go on. So this one is necessary and sufficient, and for the blue one, it has no effect here in this case on the light bulb. And I will only show you P and S, so the probability of necessary and sufficient causation, because that one really reflects an evidence for the existence of a causal relationship. Okay, so I just want to remind you what I told you in my introduction. So, because what is the current state of the art? They say, well, the physiological effect actually drives 70% of the global greening. But Vous et al., they used a different method, and which is called optimal fingerprinting, and that is somehow has some caveats. I will not go into detail here. So I thought we can overcome these caveats in using this causal theory. So now, let's see how these results look on the global scale. So here I show you relative trend in LAI, in percentage per decade. In black is the observations. In yellow is an estimate for internal variability. Then the MPI ESM ensemble is in purple, and the trendy ensemble is in green. First you see the all run, so the all forcings run, so the historical run with all the forcings, and then the one without PE, so the one without physiological effect, then the one without climate change, so no radiative effect, and then the one without CO2 at all. And what is striking, that if there's no physiological effect, there's almost no greening going on in the models. And if we have no CO2 at all, we actually see a browning in the trendy ensemble, and that might be due to deforestation. So we can calculate our probabilities from that. And we find that for the combined effect of CO2, both ensembles show high probabilities, meaning that CO2 is responsible for the change. Now, if we look into the radiative effect, the probabilities are very high. So on global scale, the models tell us, well, the greening cannot be caused by climate change. And if we look now into the physiological effect, we find high probabilities, and with high probabilities, I mean higher than 66%, and that is defined by the IPCC report as likely. And so basically, if we use, or maybe that's not what I wanted to show, okay. So also with causal theory, we get to the same, or basically to the same result that Vous et al. Did, and we find that the physiological effect is actually causing the greening. But this analysis does not take heterogeneity into account. And we know that the natural vegetation is quite heterogeneous, so what we need to do is we need to focus on different biomes. And here I show you the map again from browning and greening patterns, and you see it is quite diverse. So what I will do now is I will focus on some hotspots, and that is the tropical forests, the boreal forests, and also the tundra ecosystems. So let's start with the boreal forest. Here you see again the same plot as you did in the slide before. We see in black the observations, and here you see that in relative terms the models are overestimating the greening trend. And then you see the responses when we remove the different effects of CO2. And based on this, we can again derive our probabilities. And we see that the MPI-ESM still sticks to the physiological effect as a key driver. But now also the probabilities are increasing for the radiative effect. And for the trendy, now they already show that the physiological effect might be less important for the boreal forests, and actually that the radiative effect might be more important. If we move more into the north and look into the tundra ecosystems, we again see greening, and here it turns out that actually both of the model ensembles, they say that the radiative effect is the key driver and less so the physiological effect. So this basically means that in the northern high latitudes, the radiative effect of CO2, so basically warming, is the key driver of the vegetation greening. Now let's look into the tropical regions, and here we find that in the observations actually there's not much of a greening going on. So and the internal variability estimate is even higher, which leads to the fact that there is no attribution possible. But we still can learn something from the models, and that is the models show a compensatory effects of rising CO2. So here you see if there's no physiological effect, that the models show a browning, so a decreasing trend, and if there's no radiative effect, we see greening. So it basically means that if CO2 increases, we have these two effects that sort of counterbalance or are compensating each other in the tropics. And this is somehow getting more strong in recent decades. So here I'll only look into the last 2 decades. And something that sort of is emerging here is that in the observations, the tropics are actually switching sign and now are sort of switching into a browning phase. And so if you look into the all run or the all forcings run, we see that the models do not really capture this in the right amount. But we see that for the no physiological effect run, we see that there is a strong browning going on. So this somehow leads to what might sort of pointing into the direction that CO2 fertilization is too strong in the models and sort of compensates the negative effects of the radiative effect. And this is where I want to conclude this part. So we find that the physiological effect on global scale might be identified as the key driver, but if we look into, more at the biome scale, so at different ecosystems, we actually find that the radiative effect of CO2 is playing a quite important role. And what this study really finds out is that the tropical forests are entering a browning phase, which is not captured by the models, and that is of course something which is important for future climate change projections. And this is what I will turn to now. So the question is, in the first study I attributed the effects of CO2, or I attributed the change in greenness to the different drivers of CO2. Now the question is, can we use this knowledge to sort of reduce the uncertainty in future carbon fixation by plants? And what I do here is I compare observed and modeled sensitivities to rising CO2. Then I connect historical and projected estimates and use the method called emerging constraints to reduce uncertainty. So for the rest of this presentation, I will focus on the north, because here we can assume that what we observe is really the natural response of the ecosystem, because the direct human influence is rather minor there. And also we have quite a strong response of the system due to the amplified Arctic warming phenomenon. And I said that now I want to connect or link sort of the greening observations and carbon, but where exactly is the link? So if photosynthesis is increasing, carbon uptake is increasing, and some of this carbon will be allocated to additional leaves. So more carbon, well, more higher photosynthesis rates will lead to more leaves, but also it's true in the other way. So more leaves will also lead to higher carbon assimilation. So we have the connection between more leaves and more carbon assimilation. And this is something that we can make use of. So if we look into this CEB 5 ensemble for the projection of cross-primary production, which is basically photosynthesis, under rising CO2, we find that all the models show a positive response. So here I showed a change in GPP for a doubling of CO2, and this is the 1% CO2 simulation. So these are simulations that start at the pre-industrial equilibrium, and then every year CO2 increases by 1%, and at the state until it doubles, we check the estimates and we see, yes, the models agree that GPP will increase, but they really disagree on the magnitude. So we have a very strong uncertainty in the ensemble, and the conventional approach to handle this uncertainty is to apply the principle of democracy and say, well, each of the models are as good or as bad as the other one, so we just make an unweighted ensemble average. And in recent years, people thought maybe we can get a better estimate than just a multimodal mean. And one concept that sort of was developed in this context is the emerging constraint method. And it asks, can we use observations, and in this case, can we use the observed greening to get a better idea of the future? Or can we use it to reduce the uncertainty here in GPP projections? And I will shortly tell you the concept of emerging constraints. So first, what we need to know is what is actually forcing the system to change. And we know in the Earth system it is increasing CO2 concentrations. Then we define our predictant. So we define the variable that we like to know, and that is, at a different state of the system. Mostly it is at some point in the future, and thus we cannot observe it. So this is our predictant, and in my case it is the change in GPP. And we ask the models, how will it be? And here the symbols represent different models, and we get, each model tells us something, but we see this high spread in the projections. Now we need to define a good predictor, which is a diagnostic variable of the predictant, so they are linked. And this should be an observable entity of the system, and it should also come from a representative historical period. And this is where we use LAI from remote sensing datasets. And if we plug in the predictor, you should sort of find this intermodel variations. So a model that shows a strong response in the predictant should also show a strong response in the predictor for the historical past. And the same is true for models that show only a very weak response. Since we can observe what is on the x-axis, we can plug in our observations, and we can combine the two to then project an emerging constraint on the y-axis, so the predictant, and get a better idea of the future in this case. So as I said, we need a very strong coupling between the predictor and the predictant, and let's test our CEB 5 ensemble if this is actually the case. So here I show historical simulations, so this go from 1850 to 2005, and I show 30-year averages for changes in LAI versus changes in GPP. And here this is the blue model, the MIROC model, and it shows a strong linear relationship between the two. And now we can go through all the models, and they actually agree on the fact that there is a strong coupling between these two variables. So the CEB 5 ensemble agrees on this. It's actually linear relationship between changes in LAI and changes in GPP. So there is a strong coupling between predictor and predictant. Then we need to know what is actually forcing the system. So we know it is CO2, but for the northern high latitudes, actually temperature play a very important role, or warming plays a very important role. And here I show the standardized anomaly of CO2 and temperature for the northern high latitudes. And we find that they are strongly correlated. But we are not really interested in sort of disentangling the two, but we want to know the overall forcing that is sort of pushing the system. So we make a principal component analysis of the two time series and use the first principal component, and that explains most of the variance, not only for the observations, but also in the models. And this first principal component we denote omega, here in red. So now we can look into the historical simulations and the observations and see how LAI, our predictor, changes with the forcing omega. So here I plot LAI versus omega for all the models and the observations. And the observations are here in the middle. And you see that in absolute terms, LAI is all over the place. So you see there are models that show very low LAI and there are models that show very high LAI. But we are not really interested in the initial state. We are more interested in the response to the forcing. So what we do is we make linear fits and look into the slopes of these different fits to see how each of the model and the observations are sort of responding to the change. And we see that also here the models are sort of all over the place, and there's one model that is in the sort of in the range of the observations, and then there's another model that is really overestimating the observations. So we can use now this information and connect it with the projections of GPP I showed you earlier, and we find actually that in the CEB 5 ensemble there is this intermodal variation between the predictor and the predictant. So maybe here on the x-axis, I show the LAI sensitivity to omega, which are basically the slopes I showed you earlier. And on the y-axis, we have changes in GPP for the northern high latitudes at a doubling of CO2. So what this plot basically tells us that we have a model, here Hedgeham model, which is the purple one at the very upper right corner, and that shows a very strong response in GPP, and it does also show a very strong response in LAI. And the opposite is true for these models that show very low response. So we can use these variations and plug in the observations, here the black line, and connect the two and get an idea for where, well, and we get an observational based emergent constraint here for the y-axis, and that basically tells us what GPP will sort of increase by 3.4 petagrams per year if we double CO2, and that is an estimate we get from observations and models alike. So this is now just another estimate we throw in the ballpark, and now we want to, of course, know if this is somehow better than the multimodal mean or anything else that was reported. So we use different observations, and I use again this seasonal cycle of CO2 I showed you in the introduction. And you know, it is somehow representing the activity of the plants. And here I show the seasonal cycle of CO2 at Point Barrow, which is a station up in Alaska, and it's representative for the northern high latitudes. And you see this change here in August. So you see that, and here I compare in dashed lines the 70s with the solid lines, which is in the 2000s. And you see that actually CO2 there's, well, this minimum decreased, which points into the direction that more CO2 has been taken up. Now, the purple model, which is the Hatcher model, is overestimating this increase, whereas the yellow model, which is here the CESM, is underestimating this increase in the seasonal cycle. So it is consistent with what we find here in the emerging constraint analysis. And there's the blue one, the MIRAC ESM model, that is really getting the observations quite well, and it is also the one which is nearest to our emerging constraint estimate. So using different kind of observations, totally independent, we find sort of a consistent picture with our emerging constraint estimate that we get from remote sensing. But I said we can use this method to reduce uncertainty. So here in the PDF in red is the multimodal mean. So it's just assuming, you know, it's a Gaussian distribution, all the models have the same weight. And now in blue, it's the emerging constraint estimate, and we see that it shifts to upper values. So it reduces in uncertainty, but it also shows that it is 60% higher than what was, you know, assumed, or what was earlier, you know, basically it's 60% higher than the conventionally used multimodal mean. And this is where I want to present you the summary of this part. So can we use the greening to reduce the uncertainty? Yes, we can, and using the emerging constraint method. And I showed you that we can use CO2 measurements to sort of corroborate this EC estimates from the remote sensing product. And then I find that actually most of the models are underestimating this carbon fixation by the northern lens. And that is also a key result from this study. And this is where I would like to present you my main conclusions. So I asked, how is the natural vegetation responding to rising CO2? And actually, rising CO2 drives a divergent response of the natural vegetation. So first, we find in the tropical forest that actually leaf area is getting lost due to probably climatic changes, but also might be due to deforestation. And that indicates that this ecosystem is somehow maybe shifting to be a source of carbon, whereas in the northern high latitudes, we find that the models are underestimating the carbon uptake, and actually it might be that the northern ecosystems drive the terrestrial carbon sink, and that is, you know, still debated, but an interesting outcome of the study. And since we are here in a workshop for ecology and climate and society or economy, I thought of how can I put my results into perspective. So, you know, these three systems, climate, ecosystems, and society or economy are, you know, they are coupled. And, you know, one thing how society affects on climate is CO2 emissions, right? And you have the, you know, feedback already, but I'm not so, in my studies I did not look into this. I went further and I looked into how does then climate respond, sort of influence ecosystems, and that is due to environmental change. So we have a change in temperature, precipitation, or radiation, and that is of course have an effect on ecosystems. But the CO2 and that can of course have an immediate feedback to climate. But I also did not look into this in that time scale. I looked into other timescales, but first CO2 emissions by society or economy are also having an impact on ecosystems directly through to the physiological effect, so CO2 fertilization or the water use efficiency effect. And the ecosystems, they respond to this change. You know, I showed you they can green or they can brown. And I guess after my PhD and in this context, I really think that it is still unclear how greening and browning will sort of feed back to the climate. So will we have, so is, you know, greening sort of can influence the albedo effect. It can also have an influence on hydrology. It can also have an effect on, the snow masking effects. A lot of things we already heard today. But in terms of browning, that is sort of now being a new topic. What happens actually when the tropics are disappearing, or not disappearing, but, leaves are disappearing. So how is the response to climate there? But maybe even more interesting is how is greening sort of influencing on society. So if we look into Siberia, it's getting greener and people actually find it nice. They can even start doing agriculture where they couldn't before. And in terms of browning, if we have tree dieback, or if we have, the trees in Europe that are really not getting, they have problems with the increasing temperatures. So there might be some economic and also societal impact. And these are still, something we could discuss. Thank you very much.
Yeah, thank you, Alex, also for providing perspective on our systems at end. So, questions, Michael?
Thank you very much for a truly excellent lecture, very pedagogical and interesting.
Thank you.
I just wanted to clarify a little bit the role of Judea Pearl in this and the connection with optimal fingerprinting. Actually, I haven't read the particular paper of Vous et al. That you referred to, but the general methodology is based on something called FAR, fraction of attributable risk.
Yes. Mm-hmm.
The formula of which is 1 minus P0 over P1, where P1 is what actually happens and P0 is what would happen in the world in which the effect we're looking at is absent. And that is formally equal to the PN of so-called counterfactual causality theory, but not to the sufficient one and certainly not to the PNS.
Only necessary.
So, there's a lot of stuff based on this FAR, and there was a lot of resistance. The guy who picked up on this and pushed it in the climate world is Alexis Hanar, but there was a lot of pushing back from the people who had spent a good fraction of their life just using that one piece. Mm-hmm. Okay, so I think that it would be nice if you also refer to the paper which is a paper in the Bulletin of the American Meteorological Society, on which Alexis is a lead author, but Judea Pearl, as well as Friederike Otto, who was one of the referees of another paper and rather opposed, and myself were co-authors.
Okay, I see.
Anyhow, considering the fact that it's still sort of the basis of the major practice of
That's true, yes.
So-called detection and attribution technology, it's worthwhile mentioning that there are other ways of doing it.
You're right.
And optimal fingerprinting is coming from Klaus Hasselmann or from somebody else? Yeah, so it's coming from Hamburg originally.
Which went from a scalar ODE to linear PD instead of non-linear.
Yeah. But in optimal fingerprinting, I guess the key assumption is that correlation means causation, and that is not necessarily true. And in this causal theory approach, you sort of get rid of this problem. Yeah.
The book of Pearl is called Causality, Models, something, and Inference.
Inference, yeah.
Yes, thank you very much. A very clear presentation. I was wondering about your results of the browning in the tropics. And you try to ignore, let's say, the anthropogenic land use changes, or you excluded that from it?
Yes, so as good as I could,
or
as well as I could, yeah. It is, so you see here, when there's no CO2, we have browning.
Yeah.
And that is probably due to deforestation.
Yeah.
So there's
Okay, yeah. Because if I think if you just look in the literature on, so all kind of course there are all kind of studies who really focus on one side, and we do all kind of analysis on remote sensing analysis on not only on lever index but NDVI, etc. All kind of parameters. They only find browning trends with not that long records, I think, and so I was wondering. So my question was indeed: so is it anthropogenic land use change or something else, or is there really something happening that there is a mechanism that it has a kind of browning effect? Because some people really say that, well, we also see a browning due to limiting water resources or other nitrogen, etc. Yeah. So I was wondering what you think here.
So this is a color-blind friendly figure. So here in the Congo Basin, you see a browning trend, and there were a few studies on that. And if you check and they sort of say that it's due to a long-standing drying trend there's a long-standing declining trend in precipitation. And I checked the observations, and it's true. So I mean, you really see that there's a lot less precipitation coming. So this is why I was also surprised as you showed the figures where we have this strong increase in precip for the Congo Basin, looking into the future. And there are many attribution studies to somehow want to attribute why do we have this decline in precipitation in the Congo Basin. And they say it is not due to CO2, or it's not due to climate change. It's probably some interaction of multi-decadal climate modes and stuff like this, which is maybe not represented in ESMs very well. But this might be the reason why we have this browning in the Congo Basin. But if you look into the Amazon, there we have actually reoccurring droughts, mostly modulated by ENSO, but also not ENSO-related droughts. But a drought does not sort of lead to a browning trend, because it is like an episodic event. But actually what I found is that you have this legacy effect. So you have, for example, in 2005 there was one very severe drought, and in 2010 the next drought already came, and 2005 and the effect from 2005 were already still sort of visible in the ecosystems. So and this could lead to sort of a monotonic browning trend if you have this sort of impulses, and the ecosystem needs a couple of years to sort of recover. Yeah. So yeah.
Well, thank you for this. I had seen only half of your work, and the rest is also really nice.
Thank you.
Actually, I have 2 points. One is continuing on this. I had looked a little bit on some areas of the greening browning trends in the northern latitudes and how they would relate to results on multi-stability. And one of the things that came out of that was that, at least in the areas where there was not this uniqueness, it was not determined which state it would be, it seemed that there the trends could actually be attributed to the multiple states, but then that was not taking into account all the models, all the variables that are in the models. But on the other hand, most of these models do not simulate well the existence of alternative states. So that could be maybe something to check. And then the second thing is that I was wondering whether something like these could be combined with what Peter was talking about. So basically now there is also the OCO satellite measuring CO2 in the atmosphere. We have really high resolution data for the reflectance and for all sorts of variables through the sentinels, like Sentinel-2, Sentinel-3. We even have data for cloudy days through Sentinel-1. And I was wondering if we could maybe combine a bit these approaches and do something that includes on one side reverse modeling, on one side global modeling, and on the other the actual observations.
Yeah, I like the idea of pursuing different pathways and sort of find convergence, or testing for convergence.
Yeah, and at least see, like, okay, if we just look at the observations for the next, I don't know, 2 years, what do we get compared to what we got with models? That would be nice.
Maybe something that relates also to your research is that if you look into the boreal forests here, you find this sort of dipole response. So in the Northern American boreal forests, we see rather browning going on. But if you look into Eurasia, it's really vigorously greening. And I looked into all the studies I could get my hands on. So why is this the case? And I guess it might be, as you said, due to different species compositional
different plants. Yeah. Well, I also remember that when I looked into it for North America, I could not get any type of relationship with my results to the trends.
Okay.
Whereas for Eurasia, it was possible.
Okay.
And this might as well be due to the different plant functional types.
Yeah. But this is observations only. Yeah. Okay.
Hi, I was just curious to hear where you perceive the forest fires of recent times. This year we've heard about colossal fires in the tropical Amazon forest, in the forests of eastern Australia, and all across Asia of the old Russian Empire. Do you perceive it? What do you think its role is going to be? Does it fit in with browning?
Yes. So, fire is again an event, an episodic event, and that might, we make this Mann-Kendall test for monotonic trends, so they will be just not detected as being a trend. So if we have like a healthy ecosystem and then a fire comes and sort of destroys it, then it will not be detected as a vegetation trend here. But I guess this fire events will only lead to the case that a few of these pixels will disappear and not be...
Possibly, but on a longer time scale, you have to think that they said in Siberia there were thousands of forest fires. This is no longer an isolated event, it's a statistical event. And similarly in California now, it's been over the last 10 years, more and more and more fires. So it would be interesting to integrate them into your picture.
So there's at least, for the boreal forest in North America, also there we have a lot of...
This occurs both in the tropical forests of the Amazon and in the boreal forests of Asia.
But
these are thousands and thousands of fires.
True, yeah. But most of the tropical fires are anthropogenic. Most of the tropical fires are anthropogenic, so they are really induced by humans. And I guess the models, I don't know if they are capable of, sort of modeling that. So I don't know if we sort of can represent this in this attribution study. But I think just, yeah. Yeah, but it will certainly have a big effect on the ecosystems.
Yes. We need to vacate the room because there's going to be a public lecture here at 18:00.
Okay.
Well, it's actually...